Uh, Hi everyone. So today we have Minh Nguyen. He's a PhD student from the University of Alabama at Birmingham, and today he will present a talk and joint work with his supervisor, Dr. Rudy Weikart. The title is a Prufer angles approach for first order systems of ordinary differential equations with distributional coefficients. So please, your time, Minh.
All right. So first, I would like to thank you, Dr. Dean, Dr. Benji at Charles University for invite. Um, the talk today is my talk today is about differential equation, right? And it's with rough distribution. This is, as Dr. Dean has mentioned, this is my joint work with my PhD advisor, Professor Rudy Weigert. So, um, so first, why do we have to study all these things? So so the so everything started from the Sturm-Lewin equation. So this one is a second order equation, and you can see right here. And in particular, we're gonna pose this differential equation on interval a to b. Um, in the classical theories of the Sturm-Lewin equation, we require that the coefficient p, v, and r are function locally integrable. We also require these two conditions p and r to be positive almost everywhere. So under this condition, what going to be the solution? What is the regularity of the solution? The, reg the solution we call y will be an absolutely continuous function on a to b. It's going to be belong to the space AC. Okay, so together with this second order differential equation, we also impose boundary condition, separated boundary condition at the two endpoints A and B, as you can see right here. So this is a well-studied subject, and there has been many books written about this one. The latest one can be say maybe Zato. This is a monograph in 2005. Okay, so so Sturm theorem. So it's Sturm's theorem has a deep history. Well, it's go back in maybe 180 something years ago in the 19th century. So so basically, let's state the Sturm theorem, the three Sturm theorem in a modern version. So basically, if we consider the homogeneous equation, the Sturm-Lewin equation for, when I say homogeneous equation, I mean the right-hand side of the equation is equal to 0, right? And let's assume that we have two equations with two sets of different coefficients, P1, V1, and P2, V2. Now, if we can compare the two coefficients, P1 and P2 and V1 and V2 in this order, then we can conclude that there's at least one zero of y2 between two consecutive zero of y1. So basically, if we so let's say we have an interval a to b right here, and if this is y1, then well, okay, I should have another one over here. Let's put the Dirichlet condition at both endpoints. Okay, so these are the two consecutive zero of y1, and then they're going to be at least 1 0 of y2 in the middle. Okay, and we will also have at least one over here. So basically, y2 will also look something like this one and something like this. So so this is the so-called the Sturm comparison theorem for the SL equation. Now, if we have two equations, then we have there exists at least one. Okay, but if we only consider one equation over here, and because if one equation, we can think about one equation as two identical copy, right? So P1 equal to P2 equal to P, and V1 equal to V2 equal to V. Then we can also have exactly the same conclusion as in the comparison theorem. But then we also have a stronger conclusion is that now there is exactly 1, 0 of y2 between two consecutive 0 of y1. So basically, the conclusion that we're going to have in the stream separation theorem is that the 0 of the two independent solutions of the same equation will be interlacing. Okay, so I think this is the famous fact about the Sturm-Lewin equation. So aside from those two equations, from those two theorems, we also have the Sturm oscillation theorem. Basically, this theorem say if we choose the boundary condition careful so that we have a self-adjoint problem, then this eigenvalue problem we have discrete spectrum. Okay, all simple eigenvalue. They're bounded below, and we can sort them out in this order, and they're going to converge into infinity. We also know that that corresponding to the eigenfunction yn, we have n minus 1, 0. Okay, so basically we can count in the eigenfunction, or we can count in the eigenvalue by the number of 0 of a eigenfunction. So basically these are the basis fact about the Sturm theorem. Now, my talk today, I also, aside from the Sturm theorem, I also want to talk about the eigenvalue asymptotic of the eigenvalue. So basically over here, as you can see, we have in certain cases, we know that all the eigenvalue going to be simple, and all discrete is going to converge into to infinity. Now the question is, how fast is converging to infinity? So the earliest result regarding the asymptotic of eigenvalue go back in maybe before 1911. So it has, the formula has been known for a long time, but the first time where such a formula were given in a textbook can be, say, in 1970. So this is a textbook from Gobert and Grant. So basically, over here they consider the case, the two conditions on P and R, aside from its being locally integrable function, we also require that P and R has to be positive. So now we jump to 87, where Atkinson and Minh they prove an asymptotic eigenvalue for such a thing. Okay, so we also require that P has to be positive, but we don't have this condition anymore. So this condition that R is positive is not assumed. So in this particular case, when we admit in this particular condition on R, the positive net condition on R, it's going to be, the picture will be a little bit different. So earlier we have only the eigenvalue is bounded below and converging to positive infinity. In this particular case, the eigenvalue, we have two branches. The first branch go to, we have positive eigenvalue, and those converging to positive infinity, and we also have a set of negative eigenvalue, which I denote by lambda n minus over here, and that's one we converge into minus infinity. So that's the situation when we deleting the condition, positive condition, and we also have the same. We also have this particular asymptotic formula. I also want to mention that this formula, the formula from Gobert and Grant, is a special case for this formula. Okay, so this is the result for the asymptotic eigenvalue for Sturm-Liouville equation. Now let me switch gear a little bit and try to cast our problem in a little bit different way. Instead of talking about the second order equation, let's drain from the second order equation into a first order system. So what do I mean? So let's say we have the classical Sturm-Liouville equation minus b y prime plus qy equal to lambda ry. So over here, if I set a new variable u to be a column vector y and py prime, so we call the py prime to be the pseudo derivative of y. Okay, so basically we can rewrite this second order equation as a first order system of the size 2 by 2. In this particular case, we want J to be a constant matrix. In general, it's going to be a skew Hermitian, but skew Hermitian in 2 by 2 gonna be just simply of this particular form. So we also want Q to have this particular thing and W to be this thing right here. So basically this is the way that we sometimes use to drain from second order equation into first order equation, first order system. Now maybe as you can see, let me point it out that changing from second order equation to first order system, the up diagonal thing over here will be 0, okay, and in W as well. So we can also change in the boundary condition into this particular form, and you can see right here. So in 2001, Biden and Volkmer relaxed the condition. Well, it's not exactly relaxed, but basically they don't require any condition, the positive net condition on P, and they don't require the positive net condition on R. Still, they still require that P and R has to be locally integrable function, and they require that this number delta plus and minus here has to be non-zero. So in this particular case, they can also prove very similar to Mingarelli and Atkinson that the positive eigenvalue is this convergent to infinity and similar to the negative eigenvalue. So we have this particular formula for the asymptotic of the eigenvalue, and you can see now this particular formula is a generalization of this particular formula, right? So that's the case for the coefficient to be locally integrable function. I need to emphasize that fact because now in 89, Benefit he working on the first order system where all of these things are not function anymore, but now we are allowed to use measure, be finite measure. Now we require R to be a positive measure. Okay. Then we can also have a system of positive and negative eigenvalue, and then we have this particular asymptotic formula. Now in Bodmer, in 2005, he wrapped in the condition, positive condition R, and he also had this one. So So that's in the history of what has been studied so far. Now I move to my main goal and the hypothesis that I will adopt for my problem. In my problem, I will consider the first order system in this particular case. The matrix J right here will be the matrix 0 minus 1 1 0. So Q right here will be Hermitian or maybe symmetric, and W to be semi-positive definite. Okay. Wow. Okay. So sometimes this particular one might not be so. So sometimes we're not going to require this particular one, but basically Q going to be still Hermitian and symmetric. All right. So what going to be the difference between my setting and the classical setting? In my setting, I allow the coefficient, the entries of Q and W right here to be distribution of order 0. Okay, and I also require that there has to be a continuous measure. I will discuss later on in detail for why this particular condition is required right here. Okay, so we're gonna prove an analog version of the three theorem from Sturm, and we also prove an asymptotic formula for this particular eigenvalue problem. So that's here my main goal. So before I go into that, let me talk a little bit about what does mean by a distribution. A distribution or a spot distribution, or people sometimes call generalized function. A linear functional on this set right here. So the set of all function often continuous what is this one? Infinitely many time differentiable function, and the compact has to be support. So if this linear functional satisfy this condition, if we take for every compact subset K of the interval A to B, we can find the two numbers C and K such that this thing happen. Then we call this one a distribution. Now, then what does mean by a distribution of order 0? If we can require this number K can be chosen independently as 0 from K, then we call it a distribution of order 0. Okay, and subsequently we will denote D prime 0 to be the space of distribution of order 0. Now here we can have several simple examples of a distribution of order 0. For example, the delta distribution, the delta function, distribution of order 0. Okay, or if we are given a locally integrable function f, for this particular thing we can also define a distribution in this particular way, and it's going to be a distribution of order 0. We sometimes will identify f and this particular distribution of order 0. So sometimes if we just write in f without saying anything, then we might mean two things. We might mean it's going to be a function or it's a distribution. So another thing can be said is that if mu is a random measure, then we can also get a distribution of order 0. So here we need to discuss a little bit about function about variation and the Lebesgue measure. So over here we can define what does mean by variation, and we define a p something, right? So basically we can define the variation of the function Q on any compact set K, and if it's less than, if we see a finite number, then we call this function Q a function of locally bounded variation. We denote the set of the collection of all such functions to be BV log. For any BV log function, we can define the so-called the Lebesgue measure dq right here. So dq by itself is not a real measure, but if we restrict dq on compact subset, then it's going to be a real measure. So for that dq, we're going to define, we're going to have as similar as before. We have a distribution of order 0, this one. And so let's take one example. If h is the Heaviside function, right? So we know that the derivative, the distributional derivative of h going to be, it should be the delta function is 0. Now we can also, corresponding with this h, we also have these two distribution. So we will see subsequently. Right now is that one will be derivative of the other one. Okay, so basically we want to discuss about the risk representation theorem. Let's say for any distribution of order 0, if Q is for any distribution Q of order 0 on A to B, we can find a BB log function capital Q right here, so that we have this integral representation for every test function. So, and for this reason, we also, okay, Q, the capital Q, sometimes we also call the antiderivative of the distribution Q. So before we talking about that one, we have to say that it's really important that that distribution and function we can. So distribution is just a generalization of function in general, but there are some difficulty with working with distribution. There are some good things. Okay, so the first good thing to working with distribution that we can still define derivative of distribution, and the so this particular one is we call the distributional derivative. So if P prime is the derivative of P, right? Okay, if P is a distribution, then the derivative will be defined this way. And similarly, we also can define antiderivative. Well, we can prove that the antiderivative of distribution is this. And the difference between two different antiderivative will be a constant distribution. So there are a lot of things going to be very similar to the theory with what we have known in function. Now, as being noted here, we call the capital Q function, BB log function, exists in occur in the risk theorem to be the antiderivative of the distribution, right? So basically we can do it all interesting. And
I think phi is missing in your integral, right?
Phi? Oh yes, I should have phi right here. Yes, yes. Thank you. So we know that, so basically to summarize the discussion so far, this is what we know heuristically. The derivative of a BB function will be a distribution of order 0. And if f is a BB function and Q is a distribution of order 0, then we can define the product of these two things. So usually it's different from function, right? So if we have two functions f and g, then we can easily multiply these two functions together. But if we have two distributions, let's say Q1 and Q2, it's going to be really difficult to multiply these two distributions together. And sometimes we cannot even divide. So over here, this particular definition of FQ is really important. So as I mentioned before, we can define, we will identify a BV function with we can also identify BV function with a distribution, and Q already a distribution of order 0. So basically what we are saying over here is that we can multiply two special type of distribution together. Okay. Now for distribution, we can also have the chain rule. So we can take in derivative, and we also have the chain rule when we use derivative. So the first, I think the first chain rule is discovered by Volbert in 67, and it looks quite ugly, as you can see right here. But if we add in this particular condition, U has to be continuous, and F is a function, a C1 function, then we get back what we have, what we usually have in function, right? So this is the particular reason for why previously I say we will only consider the distribution orders of order 0, and it has to be associated with continuous measure for this particular reason. Because if we don't assume that condition, then we use the chain rule a lot, and the chain rule will be very hard to work with. So at least we have something nice to work with, and that's the reason why we have to add that. We only work with continuous coefficient. Okay, so over here, let's consider a simple example of a differential equation with distributional coefficient. Now, let's say we have on the interval a to b, let's say, and we consider this equation. This equation has to be understood in distributional sense. So on the left-hand side, we have y to be, so solution to be BV function, right? BV function, right? Or let's say we're going to look for the solution space. We have to look for solution in the BV function space. Now, the derivative of a BV function will be a distribution of order 0, so we can understand the left-hand side as a distribution. On my right-hand side, I have y to be a BV function, and mu right here will be a distribution order 0. So we can multiply these two together, and we can also think about this point as a distribution. So both the left and the right-hand side are distribution, and the equation is understood in distribution sense. Now, let's be more specific and consider the equation y prime equal to delta naught y on the interval from -1 to 1. So delta naught is the delta function center at 0. So we can look into this particular one from -1 to 1. We delete the point 0. So if we just pose the same equation from 0 to 1, then we can, because the delta distribution restricted on 0 to 1 will be identical to 0, right? Identical to the 0 distribution. So basically, on the right-hand side, we have the equation y prime equal to 0, and by the Dubord-Raymond lemma, we can conclude that the right-hand side will be a constant function, and similar to the left-hand side, we have a constant function, and we will require our solution to be balanced. What do I mean by balance? It means so for example, we say right here, y naught over here has to be the average of the value on the right and on the left side. Okay, so this is one particular, and it's a really simple example of a distribution of a differential equation for with this type of coefficient. Now, aside from distribution, we also discuss about the matrix of distribution. Then we go, so this particular thing, this particular definition is going to be very similar to what we have in linear algebra. For example, we can also define what is meant by a matrix of distribution to be non-negative. Okay, we can also define the conjugate of a distribution. We can also, well, okay, so this is the conjugate of a scalar distribution, and similar for the conjugate of a matrix distribution over here. I should say I should have the bar right here. And we say a matrix of distribution will be Hermitian if this condition is satisfied, if Q equal to its conjugate, and a matrix of distribution, and matrix of distribution we call semi-positive definite if we have this condition for every vector z in C2. All right. So this is the repeat of the system that we're going to look at. So we look at balanced solution for this first order system. The coefficient of the entries, well, the entries of the coefficient are in the class C right here. Distribution of order 0 associated with continuous measure. Now, let's talk a little bit about the main tool of my research. So in the title we have a Prufer angle approach to the first order system, right? So what does mean by a Prufer angle? So let's first consider is that the homogeneous equation jy prime plus pu. Okay, so we require the entries of P has to be distribution of order 0 and continuous. And when this, and under this hypothesis, our solution will be continuous. Our solution will be a BV continuous function. And more than that, if we consider, okay, so U will have will be a vector solution, but 2 by 2, right? So now let's try to draw on R2. So the solution U, for example, UA will be, so this is the phase space, right? So this is the phase space of the solution U. This is UA. This is UB. So basically, we will denote if, for example, at US right here, we connecting the origin of the phase space and the point US, and we consider the angle of this direction from the y-axis. Starting from the y-axis, go to the vector US. We call this one theta. Okay, so this one will be the Prufer angle. This one. And this is the basically the algebraic definition of theta. And for that one, we also have the R to be the modulus of that vector US, right? So now, what we're going to use this one for? Let's look into this equation for U equal to R sine theta cosine theta here, and we taking derivative both sides of this equation. Now, as you can see over here, we have to use the chain rule, right? The chain rule to find the derivative of psi of theta. Okay, and for that reason we use the Bornberg chain rule. So basically, we're going to have u prime. We then multiply with u j on the from the left with u prime and subtracting to pu. And after some simplification, we're going to have the Prufer equation, the first Prufer equation. We also have the second Prufer equation of R, but basically we're not going to use that one. This is the main thing that we use. So this is the Prufer equation of just an equation right here of a homogeneous equation. Now we can okay, so we should I mention that one? All right, so let's go ahead over here. So basically, we will use this particular thing to prove the Sturm theorem, right? So the Sturm theorem, first we need an auxiliary theorem for before we can prove the Sturm comparison theorem, an analog of it. So basically, let's say if we consider two equations, P1 J U prime Q1 U P1U and JU prime P2U. So over here P1 and P2 2 by 2 matrix of distribution, right? And we also require that P2 has to be greater than or equal to P1 in matrix form, as we defined before. So if we have this particular condition, then if we can compare the two the two coefficients P1 and P2 right here, then we can also compare the Prufer angle. And this is really important. And you can see subsequently that we can use this particular result to prove. Okay, so this is a stronger. This is a stronger version of the angle comparison theorem, so the only difference is that we add this particular hypothesis that P2 minus P1 multiplied with U1 does not vanish. And you can see this particular thing is a measure, and we require that this particular measure does not vanish on CD. So if we also have that one, then we can conclude that then we have a strict inequality on the angle, on the Prufer angle. So before we only have a non-strict inequality, right? So if we assume more, then we have more. So for the Sturm comparison theorem, we also consider the two equations Ju prime plus P1U and Ju prime P2U. And we also require this condition. So furthermore, we require P1 to 2. What does it mean by P1 to 2? So P1, as I mentioned, is going to be a matrix of distribution. So I have P1, 1, 1, P1, 1, 2, P1, 1, 2, and P1, 2, 2. So basically the P1, 2, 2 will be the bottom right corner of P1, and P2 to 2 will be the bottom right corner of P2. So we require that these two has to be positive measure with support going to be the whole interval A to B. Now if we, so before So in the classical stem comparison theorem, we only have a scalar solution. Now we have a vector solution, but we only look into the first component of the vector solution. Now, if we have two consecutive zero of the first component of the first vector solution, then we can conclude similarly as the classical theorem that say the first component of the second vector solution, we also have at least one zero between the two consecutive zero of the first component of the first vector solution. Okay, so we have an analog of that particular result. For the string separation theorem, we also have, so over here, instead of having two equations, we only have one equation. We can think about it as two identical copies of P1 and P2. So we can also conclude that if we have two independent solutions, two independent vector solution U1 and U2, then the first component of, then the zero of the first component of these two vector solution will be, the zero will be interlacing, or to say in a different way, between two consecutive zero of one thing, we have exactly one zero of the second thing. Okay, so for the oscillation theorem, so far the general condition we pose on P going to be the bottom right corner has to be a positive measure, right? The bottom right corner has to be a positive measure. Now, over here, for the stem oscillation theorem, we're looking at the first order system, J, but this particular one is not homogeneous. We look into this one, JQU equal to lambda W. WQ for some reason is so basically over here we have to look into the eigenvalue problem, right? For some reason my pen doesn't work, sorry about that. So we also require that we also pose the condition on the bottom right corner of Q, of this Q right here, and we also require that the support of this particular measure has to be the whole interval A to B. So we can conclude that as in the classical theory, the spectrum of the eigenvalue problem is full discrete. All the eigenvalue is simple and will accumulate only at plus and minus infinity. Furthermore, we can also, so if we say Kr to be the unit non-negative integer satisfy this condition on the Prufer angle, then we can conclude that, then we can count how many zero the first component of the vector solution will have. So over here we consider the eigenvalue problem because the vector solution has to satisfy the equation and it has also to satisfy the boundary condition at A and B. Okay, so all of these can be done using, so the main tool, as I mentioned before, we're going to deal in with the Prufer equation that we used earlier. For some reason, can use Can you hear me?
Yes, we hear you.
For some reason, I cannot.
Your movie has stopped, so you are now. Your picture is frozen, but we hear you.
Okay, so I think I need to.
Cannot turn the page anymore, or?
Yeah, my laptop is just frozen for some reason.
Yeah, we are still here, so no, don't worry.
Something happened.
Just close some windows.
I don't really know what's happening.
Okay, try to stop sharing and then share it again.
I had at the very beginning something happened on my end, and I left and joined again. Since then, it has been okay for me.
Yeah, it seems like that. Yeah. Yeah, so sorry about that. We just need to wait a little bit. We'll see if we can fix this. Yeah, he's leaving. I think it would be good. And then I think he already restarted his laptop. he told me that, after after last time he purchased a new laptop. Sergey, we don't hear you. Scab, interesting sounds from you.
Your voice is scrambled.
Can you hear me well?
Yes.
Yes.
Oh, okay. So it happens to some, but not the others.
Oh man.
Sergey sounds like me.
You're talking. It's like kids talking. All scramble.
Yeah,
I think the technology mess up.
Yeah. Yeah. So
I like Zoom better, as a matter of fact. I like Zoom better than Team.
yeah, it's easy to work with Zoom.
Yeah.
we are using Zoom and we haven't had such problems. So
yeah, usually we don't have
I
any.
don't know whether it's the technology or.
Do I still sound funny?
No, it's good.
Good.
I did what Minh did, just checked out and checked in again.
Yeah, that works.
He didn't check in again yet.
Yep.
Yeah, he's in.
Let's admit him.
Okay,
Yes.
so I need to start my laptop for some reason. Okay, so let me share my things again. Okay.
Yeah.
All right.
Oh, I'm so sorry about this. So where I am right now. So let's say I think we have finished this slide, right?
Yes.
Yeah.
Now let's see. I still have around 5 minutes for the asymptotic eigenvalue. Okay, so let's do this one real quick. So basically we want to get. So let's look into what we have in this in the asymptotic formula that we have in the classical situation where we have only function. Now, as you can see right here, what we have right here is that we have R and we have 1 over P, a function, so we can multiply these two things together. But as you can see, if we just have a measure or distribution of order 0, then it's really difficult to, then we cannot even define the multiplication of these two distributions, right? Thing here, you can see here and see here, right? So for this particular difficulty, we need to change a little bit. So now let's discuss about the Lebesgue decomposition of Lebesgue decomposition of a measure and the radon-Nicodim derivative. So if we have a complex measure lambda and we have a positive measure mu, then the Lebesgue decomposition will be in this particular thing, right? So we have this is absolutely continuous measure with respect to mu. This is a singular measure with respect to mu, and this is a singular measure with respect to mu. We also know that this is continuous, the lambda SC to be continuous and the lambda D to be a discrete measure. Okay, so different from before. So usually in the textbook, when we define the radon-Nicodim derivative, we require lambda over mu. We require that lambda has to be absolutely continuous with mu, respecting to mu. But over here, we relax our notation a little bit by not requiring that condition. So we can still define such a thing by just saying we take the Lebesgue decomposition, we take the absolutely continuous part, and we define the new radon-Nicodim derivative by just the normal radon-Nicodim derivative of lambda AC with respect to mu. Okay, and sometimes when we write the absolute value of lambda right here, we mean the total variation measure of this particular measure lambda. Okay, now we also want to do thing with in the matrix setting of distribution. So we have 2 by 2 matrix of distribution, all equivalent matrix value of measure, right? Because distribution of order 0 connecting with local measure via the Ries representation theorem. So we will define a measure that I denote square root of that W right here. So this one will be, as you can see, the first part will be the square root of some function, right? The thing right here will be the radon-Nicodim derivative of W11 with respect to W12 subject to the radon-Nicodim derivative of 12 with respect to W22, and then we square. So the first part right here going to be a function, and then we multiply with a total variation measure. So this thing, the whole thing will be a measure. Okay. I also want to take note that even though I write this particular object as the square root of determinant of W, we don't we don't define this object, determinant of W. Okay, so we don't define this object, we can only define the square root of it. And the square root will be a measure. So subsequently, with this, associating with this particular definition, we also define the two set P and N right here to be, we will call the positive set and the negative set of this matrix of distribution. So what we're going to use these two definition for, we basically say, if we consider the eigenvalue problem, Ju prime plus Qu equal to lambda Wu, and U has to be at 2BC at A and B. Okay, and we require that each entries of Q and W are in C, as we always do in this particular, in my talk, and we require that this particular thing, the number delta of W to be the integral of this measure. So this is a measure. The square root of the determinant of W is a measure. This is a measure. We taking the integral over the set, the positive set. This one should be minus. If we require that this particular number delta W to be positive, then we can conclude that the eigenvalue problem right here with the two given number alpha and beta, the two angle at A and B, has countably many positive eigenvalue lambda. All of these eigenvalue converging to 0, and we have this particular formula right here. So as you can see, this particular thing is again a generalization of the Mingarelli and Atkinson formula for the asymptotic eigenvalue. And okay, so I think my time is up, so let me end my talk. Thank you for your attention.
Yeah, thank you very much for choosing talk. Now, let's wait for questions from the audience. Do you have any questions for our speaker?
Just a quick question. I know there is a group of people in South Africa who is doing Prufer angle approach, like Bruce Watson, Sonny Curry. Any comments on that? I haven't followed their work closely, but it looks like what you're doing is somewhat similar, like main oscillation theorem and eigenvalue, asymptotics, all that. So, any comments?
I might. It's interesting to know. I may need to look them up. I'm sorry, I don't know about.
Yes, Bruce Watson. I think they're students, like PhD students now. Maybe Rudy.
Okay.
Yeah, I know Bruce.
Yeah.
So maybe Dr. Waikan has some comments on this talk.
That's what you get.
Oh, I have more comment, but I have a question for you,
the
Sergi.
Concerning the content, I think it has been a tough problem, and to work all these things out in terms of measures and distributions when one is so used to working with functions. And I think Minh had some fantastic ideas in order to get this job done. So maybe that would be my comment right now. There maybe another comment. There are lots of things still to be done in this respect. So we just discussed the other day, and we see there are some questions which can at this point not be answered. In particular, maybe when the measures aren't continuous anymore, and then you get these jump discontinuities in the solutions, and then you have this problem with Olpert's generalized chain rule, and that messes the Prufer equation completely up. And I guess in that case, one would need some new ideas about how to approach this even. So there are many interesting questions open, I think.
Okay. I think TY has a question, right?
Oh, it's non-academic. I just want to ask how Sergey's family is doing in Ukraine or Russia because of the conflict.
Good question.
Well, I don't have anybody left there.
Oh, okay. All right.
So yeah.
Yeah,
Yeah.
let